Hello and welcome to the last lesson, and it's been a long run in the forces topic, and we're going to look at changes in momentum. This is a physics only topic and it's higher only. For the lesson then you're going to need a pen, paper and exercise book, calculator, and unless you're needing to watch this video on your mobile phone, make sure it's off and out of the way. Try and avoid any distractions that you can. Calculator out for the starter. Straight away we're going to be looking at momentum. I'm going to give you 2 minutes. There's 2 calculations to do. Just a reminder, momentum equals mass times velocity. Halfway through your time, should we just getting on to number 2? Let's see how you've done then. Number 1, momentum is mass times velocity, so substitute in 26,700 for momentum equals 1,200, that's the mass times v. So v must be 26700 divided by 1,200, which gives a velocity of 22.25 meters per second. If you put it to 3 significant figures, you would have got 22.3 meters per second. Number 2. Again, momentum, mass times velocity, substitute in 0.002 kilograms meters per second equals the mass that we don't know times velocity, which is 1.8. So the mass is 0.002 divided by 1.8, which gives you a mass of 0.00111, it's one recurring, kilograms. If you put it into grams, that's 1.11 grams. Okay. First outcome is to explain Newton's second law, is to explain how that's linked to the rate of change in momentum. It's just a different way of looking at Newton's second law. And the other outcome is to use this way that we look at Newton's second law to talk about safety features, to apply them to safety features and how they work. For example, car airbags. This seems like a bit of a daft question, but what I want you to do, I want you to try and answer it in a specific way and not say something like it's because they're soft. What does it mean when something is soft? What is it doing that means that the force on you is smaller? Because if you feel pain because you're falling on something, it's because of the force that's been caused by that stopping, that changing of momentum. So don't say it's soft. We need to talk about how the force is linked to momentum, and that's what we're going to move on to. So I'll perhaps ask you that question later in the lesson. We'll take the opportunity now just to look at Newton's 3 laws again and make sure that we remember them. So we've got Newton's first law that says that every body continues in a state of rest, so everything will just stay still, or in a state of motion in a straight line, so moving at a steady speed in a straight line, unless acted upon by some external force. So unless you've got a force, a body will either stay as it is, stationary, or stay moving at a steady speed. So that's Newton's first law. So we'll just write steady speed or stationary with no overall force. Newton's first law. Newton's second law, which we're going to look at in a bit more detail in a minute. Newton's second law, which the easiest way of remembering Newton's second law is that force equals mass times acceleration, which will tell you then that the acceleration depends on the force and the mass of the object. So the bigger the force, the greater the acceleration. So we could write that as force is proportional, directly proportional to acceleration. So if you double the acceleration, you double the force. Or the acceleration is inversely proportional to the mass. So if you double the mass of an object, its acceleration will half. It's inversely proportional. But because mass and acceleration are linked to momentum and change of momentum, you can look at it in a different way in terms of momentum, and that's what we're going to do in a second. We'll come back to that. A reminder of Newton's third law. Action and reaction are equal and opposite, or you might have seen that before as for every action there's an equal and opposite reaction. In other words, for every force there's an equal and opposite force. So if you are sat in a chair, you've got gravity, your weight pulling you down, so there's a force on you, but also because the chair is stopping you moving, there's also a force from the chair onto you, which is how you feel that you're sat in a chair. You know you're sat in a chair because you can feel it. So for every force there's an equal and opposite force. Let's look closely and more mathematically then at Newton's second law. So F equals m times a. So we start with that. But we also have another equation for acceleration. I'll put an arrow there. So acceleration is the change in the velocity over the time taken. You could write that as v minus u, so that's the end velocity minus the start velocity divided by time, or the change in the time. So acceleration is change in velocity over time taken. Now mathematically there's another way of writing that means the same thing, which is where the letter delta, Greek letter delta, comes in. So you could write acceleration as delta v over t. When you see that letter delta in your head, go change in. So acceleration is the change in the velocity over the time. Okay, so we've now got two equations. We've got that one and we've got this one. What I'm going to do now is I'm going to substitute in. So instead of writing F equals m times a, I'm going to write F equals m times delta v over delta t, because delta v over delta t is the same as a, it equals a. Let's write that then. F equals m times a, delta over t. So the mass equals the change in velocity over the time taken. That means the same thing. Well, we can go one step further here. It doesn't have to be the velocity that changes. Sometimes the velocity stays constant, but the mass can change. And that could be, say, from a water jet where you've got a mass of water that's moving.
and the mass is changing, or a rocket where the mass is changing. So another way that we could write this is the force equals not just the change in the velocity over time times the mass. We could write it as the change in delta mv, I'm just going to put that in a bracket now to make it easier, over t. So let's have a look what that means. It means that the force equals the change in the mass times the velocity, so it could be the mass that changes or the velocity that changes or both that changes, divided by the time, which then gives us a third equation, because m times v equals the momentum, which we use the letter p. So m times v is momentum. So what this equation means is the force on an object equals the change in the momentum over the time taken. So force equals change in momentum over time taken, or the rate of change of momentum. And sometimes you'll see Newton's second law written like that. You certainly will at A level. So at A level you might say for Newton's second law, the force is equal to the rate of change of momentum of an object. And we'll put some numbers in some different situations and just check you can put those in. Now at this stage the most important thing is probably that you understand what I've done. So I'm just going to quickly go through it again. We start with F equals m times a, which is an equation, Newton's second law, that you need to remember. You need to recall it and use it. But because we know that acceleration is the change in velocity over the time taken, we can, instead of writing a, we can write delta v over delta t instead of acceleration, which gives us this one here, F equals m times delta v over t. Remember, delta means changing. Now, it doesn't have to be the change in the velocity. It could be the change in the mass or the change in the velocity. So if we put mv in a bracket there, we've now got delta mv, which is the change in momentum. Now, the change in momentum divided by the time taken is the rate of change in momentum, how quickly that momentum is changing. I'm just going to leave that on the screen for 20 seconds, 30 seconds. I suggest that if you've not done that as I've gone along, you make a little quick note of what I've done. Later on in the lesson, I'm going to get you to do that again in steps and just see if you can put it through with a little bit of help.
The force then equals the rate of change of momentum, or the force equals the change in momentum divided by the time taken.
I'm going to look now about thinking about Newton's second law as being rate of change in momentum. So I've got this rider, I'm going to give it a shove. I've marked 2 lines on there that are 1 metre apart. So I'm going to use a stop clock to measure the time, which will mean I'll be able to measure the velocity that it's going at. So it's going to have steady velocity, or it should be, because of the air track. And we're going to have a collision here where it hits that rubber band. The rubber band is going to force it back in the other direction. So we're going to have a change in momentum, and the change in momentum will be the difference between the momentum that way and the momentum that way. The rate of change of that momentum is going to be the force from the rubber band. Now, what I'm going to need to work out is the amount of time that it's in contact with the rubber band. Now, I'm going to use that by doing the video in slow motion at the end. So, get my stop clock. Okay, 0.21 seconds. Going to look now.
there's the equation that we're using. So force equals the rate of change in momentum. So the momentum before equals mass times velocity. What I've done there is I've calculated the momentum before. So the momentum before it hit the rubber band. So the mass was 0.2 kilograms. I timed it over 1 meter. So that 1 divided by 0.21 is distance over time. So that gives us the velocity. That gives us then the momentum before it hit the rubber band as 9.6 kilogram meters per second. So it hits the rubber band, goes back in the opposite direction. So the momentum afterwards is going to be minus 9.6 kilogram meters per second. So that change of momentum there is due to the force from the rubber band, the force provided by that rubber band. We can then work out what the change of momentum is. So the change of momentum is the difference between the momentum before and the momentum afterwards. So what we've got there, we've got the change in momentum is 9.6 minus 9.6. So it's gone from 9.6 to minus 9.6. So it's changed a total of 19.2 kilogram meters per second. So that's our change in momentum. Now we just need to know the time that it's taken place. What I did was played this in slow motion and worked out that the time that it was in contact with the rubber band there by freeze framing it is 0.23 seconds. So it's changed, the momentum has changed 19.2 kilogram meters per second, and it's changed in 0.23 seconds. So 19.2 divided by 0.23 gives 83 newtons. So that 83 newtons there is the force from the rubber band. So the force from the rubber band, 83 newtons, changed that momentum by 19.2, and it changed it in 0.23 seconds. So the change in momentum and how quickly that takes place is related to the force. Two minutes for you to have a go at one now. This time it's a cricket bat. I won't read it, I'll let you get on with it. Let's see how you've done. Negative momentum means that the ball's now travelling in the opposite directions. So momentum is a vector. Momentum is mass times velocity. Mass isn't a vector, so it's the velocity that's given it that vector component. If you end up with a negative momentum, it means that it's now in the opposite direction than it was initially. Force on the ball from the cricket bat, so we use that equation. So we need to find the change in the momentum and divide that by the time. So we know the momentum is going from 26 kilogram meters per second to minus 10. So we know that that is a change of, be careful, 36. So 26 minus 10 is going to give us 36. And that's divided by the time that the cricket ball is in contact with the bat, because that's the time that the force is acting for 0.1. That's why in sport you're encouraged, as part of your technique, to follow through. If you're playing cricket, you try and move the bat straight through the ball so that it's in contact with the ball for as long as possible time. It's the same in golf, it's the same when you're striking a football. You're trying to remain in contact with the ball for as long as possible, because that way you give it the greatest force. So that's 36 divided by 0.1, which gives you a force of 360 newtons. 4 marks if you've got that right, including the unit of force in newtons. We're going to apply the physics of what we've done so far to car safety features. So we've got a crumple zone. A crumple zone is an area of a car that's designed to controllably, sort of controlled collapse. So it's not meant to rigid, it's supposed to slowly collapse. The idea being that you can reduce the forces involved on the people in the car. There are other safety features like airbags and seatbelts to an extent, are all designed to reduce the amount of time that it takes you to stop, to lose your momentum. If we use what we've already used in the lesson, the force equals the rate of change in momentum from Newton's second law. If we want to reduce the force on someone involved with an accident, we need to reduce the rate at which momentum is changed. If you're in a car accident, you've got a certain momentum because you're traveling at a certain velocity. We can't, if you have an accident, change that amount of momentum. It's going to be a certain amount, because it's going to go from the momentum you've got before the accident to 0 when you've stopped. What we can do, though, we can try and increase the time that this occurs. Looking at that equation, the bigger the time there, the smaller that the force will be. So by increasing the time that this momentum is changing over, we can decrease the force on the people involved with the accident. Using the same physics as I've just used, I want you to explain the following situations. 2 minutes. Let's see how you've done. Both answers are almost identical if you've done it right. So number one, helmet helps when you fall off your bike. So we're looking at the force on your head when you, say, impact the pavement. So you impact the pavement, your head has got a certain amount of momentum as it's moving, and then that momentum, as it comes to a standstill, as it smacks on the pavement, is going to go from that momentum to zero. But the force depends on how quickly that momentum changes. So if your head hits directly the pavement, it'll stop very suddenly. So what a helmet will do, it will slightly crush with the polystyrene lining as it hits. So what it will do is, instead of your head, say, stopping in 0.01 of a second, it might stop in 0.1 of a second. It stops in a greater time. So because the time is greater, then the rate of change of momentum is less, so the force is less. If you have quite a bad accident in the helmet will need replacing. Number two, airbag. So the airbag inflates. It inflates but then starts to deflate. So when your upper body and head comes into contact with the airbag, it will be being decelerated more slowly. It's not just suddenly stopping, it's stopping over a bigger period of time. So the time that the head is stopped is increased, which means the rate of change of momentum is decreased, which means that the force is decreased. Exam question then. 2 minutes, off you go. You should be almost finished if you know what you're doing. The calculations don't take you too long. A then. It's got direction as well as magnitude because it's a vector. Part B. We need to use then that the force equals the rate of change in momentum, or the force equals change in momentum over time taken. So we calculate the momentum, which is going to be 1,200 kilograms times 9 meters per second. So that's the momentum it starts with. The momentum after the accident is going to be zero. It'll be stopped eventually. So the change in momentum is 1,200 times 9, and we divide that by the time taken. So we divide that by 0.2. That gives you a force, if you've done it right, as 54,000 newtons. 2 marks if you've got that right. Well done. Part C then, another 2 minutes. Okay then, exactly the same as we've done before. There's your starting point. Force equals rate of change in momentum. So it increases the time taken for the head to stop, which means it decreases the rate of momentum, which reduces the force. There you go, 1, 2, 3 marks, straightforward. Everyone's the same. It could be why an egg doesn't break when it's dropped in the egg box, but it does break when it's dropped without the egg box. Well, the egg box will slightly crush on impact, so it increases the time taken for the egg to stop, which decreases the rate of change of momentum, which reduces the force on the egg. Really easy. As long as you know how you're answering these questions, you just answer them the same way. I'm going to leave you then with the last summary for forces. So we've got F equals ma, we've got the version where the force equals the rate of change in momentum, or momentum over time, and then a little bit there on one application, applications, how the applications work. So well done for working your way all the way through forces. I'll see you next time for a different physics topic. All right.